Now the main point of the previous slide is you can get to this equation here, equation 4, and you can write this down in terms of numbers and words, and I think it's actually easier when you see this combination of numbers and words. So what you have for this F statistic is it's the difference in the R squared value, difference in the residual degrees of freedom, and then it is all over 1 minus the R squared value for the larger model over the residual degrees of freedom for the larger model. Okay, so things are slightly different this year because there isn't a formal written exam. So ordinarily, I would give you equations 3 and 4, and it would just be up to you in terms of which formula you remember and how you sort of apply it. Now, so much here really the main point is that you can write this equation and these manipulations in terms of the S statistic and the R squared statistic in words, and it is just as directed on equation 4, the difference in R squared over the difference in the residual degrees of freedom, and then all over 1 minus R squared for the larger model over the residual degrees of freedom for the larger model. Okay, so I'll give you some more practical examples, but first I wanted to sort of show you, if you use the formula in equation 4, where the F-test automatically reported by R and E-views comes from. So I wanted to revisit then this F-test for overall significance that is performed as the default choice in both R and E-view. So you start with the model 0 being the simple model where the Y variable is just a constant term plus some random error, and then the model 1 has these X variables in it, and you want to test the hypothesis of overall fit. So you want to test the hypothesis that at least one of these X variables have an impact upon the Y variable. So you form the F statistic as we showed you on the previous slide. So it's the difference in the residual sum of squares over the difference in the residual degrees of freedom, all over the residual sum of squares for the larger model, divided by the residual degrees of freedom for the larger model. Now the difference in the residual sum of squares is going to be the total sum of squares, and then this is multiplied by R squared minus 0, precisely because the R squared value for the larger model will be R squared. The R squared value from 0 in this case will be 0. Difference in degrees of freedom, so this is just the difference in the parameters. P parameters and the model 1, so model 0, this is be P minus 1. And residual sum of squares for the larger model will just be total sum of squares times 1 minus the R squared statistic. Residual degrees of freedom will be N minus P. Now, first P minus 1 and the S statistic will match the first degree of freedom on the subscript. Second N minus P will match the second residual degree of freedom in the subscript of the S statistic. I now wanted to try and give you some illustrative examples. So what this is intended to demonstrate is that the extra sum of squares is indeed quite a general concept. So it's not just an extension of some of the things you've seen before in the last lecture, but it will actually apply to quite distinct examples. So we've got two examples here. Now the first example I've said there is an F-test for joint significance. So this is an F-test for joint significance when you have a multiple linear regression example, so it's possible that this might be the more useful example with respect to things that you might see for a dissertation project or for other practical dataset examples. I also wanted to give you an example though of an F-test in polynomial regression, and actually it's a quadratic regression. Now the interesting thing here is that you can fit a polynomial regression model, here a quadratic regression model, just using the theory and the coding of these linear regression models, because even though the thing can be quadratic in X, it's still linear in the parameters. Okay, and again it's worthwhile to show you here just the range of examples that these regression models can be applied to. Okay, so the first one of these most useful, the second one just to sort of show you there's a lot going on in the subject. So with this multiple linear regression example then, so I wanted to try here and show you how to interpret results from a multiple linear regression example, try and get this to be as sort of practical as possible. And this is an example from the classical Longley dataset. So it's a famous dataset, sufficiently famous to have its own name. And the overall aim here is to explain the number of employed people in the US in terms of the gross national product, number of unemployed, the unemployment rate, the non-institutionalized population over the age of 14, and the yearly time trend. So in the last lecture, what we did was performed a sequence of individual t-statistics to test the individual significance of the various parameters, and the suggestion there was that both x2 and x5 can be excluded from the model. And now what we want to do, sort of using this hierarchy of tests, a more systematic f-test approach. So based on what we saw in the last lecture, we want to see if both x2 and x5 can be excluded from the model. And there is a sort of hierarchy here, so the t-statistics can sort of give you an indication of what's going on, but really it's the f-statistic which is the most systematic and best way of testing this hypothesis. So lots of potential things that could affect them will be present, however. So same set of commands as you've seen before, and I just wanted to sort of go through this because it's a certain rhyme and rhythm that you need whenever you're inputting data into R. So the data is in the file longley.txt, available from the module canvas page. And my suggestion is that you save this onto your USB stick so that the next stage when you use the read.table command, file path as short as possible. And how this works is that the shorter the file path, the more likely you are to get this correct and less likely you are to make a mistake. So how you would do this, so table applied to this file path, you call it longley, you have to use below. And the way these sets of commands are working is that for x2 you'll call in the first column of this set, x3 the second column, x4 the third column, 5 the fourth column, x6 the fifth column, y the sixth column. And just to recap, if you save it into a USB stick, you need to make sure that you have the drive letter correct. So on my computer this was drive, your computer, in which case you need to make sure that you have the right letter in this read.table command. It may not be E that you need when you do this on your own computer at home. So once the data has been entered, the idea would be that the R code would work the same way as before. So remember, you've got this separation in terms of the computational step and then getting R to show you some results. So the first thing you do is fit the unconstrained model using this thing here. So call it a name, the simpler the better. So here I've just called it a.linear model. This is a linear model, y related to these things here, x2, x3, x4, x5, x6. You have a plus sign to link all these x variables together, and then you would fit the model by simply including x2, x5 in the above. So call it something else, but simple. So b.lm, so simple name, it's not repeating this here, and this is the model y related to x3 plus x4 plus x6, again designed to sort of link all these x variables together. And then the f test using the extra sum of squares principle can then be performed using the command ANOVA. And how this would work would be ANOVA, so one of the two models x second linear models object, and then you want test equals f. This thing runs the f test. Okay, and I mentioned analysis of variance briefly in the last lecture. Actually, I think that this ANOVA command is essentially all you need in terms of the analysis of variance. Results in R, when you do it, look something along the lines of this. Now, the key thing to sort of do here is sort of, and what you would need is just this p-value at the very end, which is 0.1026, which is bigger than 0.05. So the conventional way of interpreting this is that since the result is non-significant, precisely because the p-value is 0.1026 greater than 0.05, this gives statistical evidence that x2 and x5 can be included from the model. So the interpretation of this is that the extra sum of squares provided by the variables x2 and x5 is not necessarily greater than you might expect to happen just by chance. Okay, so The extra sum of squares is just a sort of statistical terminology for information explained by the model. So in this case, what we have, precisely because this p-value is bigger than 0.05, the information that x2 and x5 provide is no greater than could occur by chance. So in this case, you could conclude that you could reasonably exclude x2 and x5 from the model because you've got no evidence that these actually provide you with a significant amount of information once the variables x3, x4 and x6 are included in the model. I wanted to try and reconstruct the f-test by hand. Now, one of the problems here is that R is a bit too efficient in some of the rounding that it does when it presents some of the results, so there is some inevitable rounding error when you reconstruct the results by hand from first principles, but hopefully you can sort of get the right basic idea. So if you do summary A.lm and summary B.lm, the R-squared values of 0.9955 and 0.9928, but the R-squared values are higher for the larger model. This also, when you run the summary command, tells you that the residual degrees of freedom are 10 and 12, so 10 for the larger model, 12 for the smaller model. So the S statistic then, difference in R squared is just 0.9955 minus 0.98. Difference in the degrees of freedom is just the difference between 10 and 12, 2. Minus R squared for the larger model is just 1 minus 0.9955, and you've got the smaller value here, 10 residual degrees of freedom for this larger model, and it gives you an F statistic of 3. Now, when R does the exact calculation in inverted commas with no rounding, it gives you a value of 3. So there is some rounding error, precisely because in this case R is so efficient in giving you the rounded answers at the very end. Okay, so it's a bit regrettable that for teaching, but hopefully you can sort of see here how the thing would be constructed by hand from first principles. Second example I wanted to sort of talk through here. So originally where this data set came from is I was writing examples for a textbook, came across this data set in a newspaper, and I wanted to see if with 8 years of maths training at university I would come to the same conclusion as these journalists. So the data from a newspaper gives a percentage of divorces caused by adultery as a function of the year of marriage. The original analysis claimed the divorce risk peaks at year 2, then decreases thereafter, but I think there's some suggestion this conclusion is misleading. So I think here, almost a non-statistical thing, healthy skepticism is probably the most important skill in the era of big data and fake news. So if you translate this into statistical terms, I wanted to test originally whether a quadratic model offers a better fit to this data than just a straight line 2-variable regression model. And from a teaching perspective, the example is also interesting as it shows that a non-linear model in X, here a quadratic model, can still be fitted as a linear regression model with the same maths and the same computer coding, precisely because it remains linear in the regression coefficients beta. So what you've got here is a subject that's quite broad and contains all sorts of different elements. So this is the original data set then obtained from the newspaper. So what you have here is the set of years of marriage, and then for each year of marriage you've got the percentage of divorces that are caused by adultery. And as you might expect, these are sort of generally decreasing over time, and the original analysis claimed that once you'd got over the second year, essentially that was the peak of the divorce risk as far as adultery was concerned. And just wanted to sort of give a simple regression example to sort of see if this relatively naive interpretation of the data from the newspaper actually holds up to rigorous statistical analysis. So I suppose I can't deny part of my original motivation was just to check that after 8 years of studying maths at university, I would do a better job of analysing a data set than these journalists. Okay, but the serious point here is I think it's a sort of interesting numerical example. I don't think regression is necessarily too sophisticated subject to analyse this data, and I just think it's also interesting as you probably you have an indication here that statistical analysis and data analysis will become an increasingly large part of journalism. Okay, and that's something that's happened in my professional career.